Our next talk is going to be an information-dense double feature. The title in the program is How to Run Your LLM and How to Benchmark It. The first subtalk is going to be Hosting AI in-house, the TNG GPU cluster story. So as a small organizational remark, we'll have a first talk for 20 minutes, then we'll have a short Q&A session of 5 minutes, and then another talk, 20 minutes, with another short Q&A session. So in the first talk, Benjamin and Lucas are going to take you on a journey on the TNG GPU cluster story. Benjamin and Lucas both have a background in physics and are nowadays senior consultants with TNG. They are responsible for the smooth operation of TNG's very own GPU cluster. Benjamin also works on developing modern language models, and Lucas serves as a point of contact for various AI services. And I guess without further ado, welcome our speakers.
Yeah, welcome to this AI double feature. Let's get started with the TNG GPU cluster story. We're going to talk about today how we operate the cluster, what we even mean when we talk about our cluster, and some special challenges that you need to know when you run your own cloud. So what's the TNG GPU cluster, or as we like to refer to it, Skynet? At the moment, that's 9 nodes with 8 GPUs each, because that's about as many as you can put into one single machine. There's our GPUs of different variety, and we operate the entire thing as a bare metal Kubernetes cluster. At any given time, there's about 10 large language models that we serve. Often they change because of recent demands, or if there's a new model, we want to quickly try it out. On top of that, there's a bunch of extra services, such as image generation, transcription, text-to-speech, and things like that. All in all, we have about 100 use cases that we support with the cluster. Every day, we produce about 15 million output tokens. Actually, I think these days it's more like 30, probably more today, because of the showcases that we have. I guess AI itself doesn't need to be motivated these days, but it's a fair question to ask, why would we do this in our own basement? There's actually many reasons for that. One of the biggest reasons for us was experimentation. We just wanted to do it. We needed to know how to operate such a stack, how we get our hands dirty. And it's also good to know when a customer asks, OK, how do we deal with GPUs? We can say something for it. The second thing, and it's also a big factor, is data privacy and sovereignty. So when we have, for instance, customer code, and we cannot just simply send it to a cloud, it's still nice to have the productivity tooling that the AI tools give us. And we take that very seriously. So one core promise of Skynet, for instance, is that we just use data for AI stuff, and we don't log anything, and we don't store any data in our cluster. Another thing is that the data sovereignty part, so if we were dependent on a cloud hoster, we are at the mercy of pricing and availability. And yes, I'm looking at you, AWS. So it's nice to have this control. Another thing is costs. On the token basis alone, it might pay off to have this on your own basement. And also, if you want to rent hardware, like a cluster of H100s, for instance, it might be cheaper in the long run to actually host this in-house. So now, that's what we have. The question is, how and why did we come about it? And all of that started a few years ago when some AI enthusiasts at TNG got their hands on some RTX. Probably some of you know this type of consumer hardware. It's relatively cheap. It's good to get started. And especially for the RTX 4090, they have about 24 gigabytes of RAM. So it's enough at the time to host the state-of-the-art models. Those have been 7 billion parameters, or 8, like Falcon. And early coding models have also been hosted with that. Modern models are quite a bit bigger than that. We cannot use it for those anymore. But we still use those RTX for services like image generation and transcription and things like that. So they're still heavily used to that. A little bit after that, people realized coding assistants are quite nice. So we needed to scale up a little bit. And we actually bought the first H100 node. This is quite a bit larger. It's 80 gigabytes of RAM and much more memory bandwidth. So that's actually quite usable for inference, which is the main use case that we have. And on two of those, for instance, you could host the most popular model at the time, Llama 2, at 70 billion parameters. That takes about 2 of those H100s. Of course, more is always better. So 2 of them just basically holds the weights. If you want to have more context and more parallelism, you want to do 4 or even 8, so that a lot of parallel requests come in. That was also about the time when Taya, TNG's AI assistant, came into the life. So a lot of people started to use the hardware, and so we needed to scale up even more. So we added up more H100 nodes, more RTX nodes, and even a third H100 node with this little asterisk. This is a special type of thing. So it's, instead of 80, has 94 gigabytes of RAM. And actually, that helped us a little bit, because with this, with the most popular model at the time, Llama 405p, I think it was Llama 3 at the time, that wouldn't have fit on a normal H100 node, but it fits on this special type NVLink node. And for a long time, these H100s have been state of the art, and those were the predominant models on the market. But earlier this year, new NVIDIA models came up, the H100, and of course, we immediately had to have it, so we bought the node, and it's nice, it's larger, it's about double the size, not quite than the H100s. It's inference optimized, and it hosts our default model most of the time. But surprisingly, also AMD came into the picture. So we had the chance to look at AMD node that was provided to us, and we did some assessment, and what we found is that the AMD chips, at the time it was an ME300, was competitive, if not better, than the H100s that we had so far. And that is not only in terms of throughput, but also for the software stack. So NVIDIA uses CUDA, the AMD version is ROCm, and that is also competitive. So after a while, we decided to also buy an AMD node, which is quite nice. At the time, this is mostly used for research. And most recently, we got our hands on new RTX models. Those are, again, consumer hardware. We're still assessing how well they operate. They are cheaper than the data center grade ones, but they also give pretty good performance, and we're still assessing them. All right, so you see, that's the current status. There's a lot of different hardware involved, and actually, this is something that occurs almost naturally, right? It's hard to avoid. First of all, we want to try new stuff all the time, and we don't want to buy yesterday's GPUs, and also availability is a question. The problem that comes with it is these things are rarely fully interchangeable. It's not only because of the memory configuration. So if I have a model that just now fits on 8 larger ones, I would have to look for multi-node cluster setup and stuff like that. But also in terms of fit, because some workloads are better suited on one node than they are on the other. So that's one problem, which gives us some sort of scheduling issues. The other thing is, it's really hard to get redundancy per model. So if one H100 costs about 30K, it's very hard to argue for a staging system that just has an infrastructure for 30K lying around. So basically, that would be a really expensive staging system. We just don't have any. So spoiler alert, we test in prod. And one of the reasons why that works so well is that we actually treat Skynet as a platform. So far, we talked about GPUs and models, but that doesn't mean it's an AI platform. And one excellent platform tool, actually one of the easiest way to do this, if you ask me, is Kubernetes. It abstracts away a lot of complexity that we otherwise would have to deal with, and lets us focus on actually operating it. And our setup is shown here on the right. So we have a bunch of different personas that interact with our setup. And with this GitOps setup that we have here, what it means is that the configuration is defined in a Git repository and synchronized by an agent, in that case Argo CD. And with this GitOps setup, it's easy to separate these personas and to not block each other while we operate. For instance, the cluster admin does low-level stuff via, for instance, the Kubernetes API or the repo. If a developer wants to push the newest version of the service to production, we just need to do a merge request, and users just interact via the APIs that are exposed. Actually, I would argue Kubernetes is the perfect platform tool for AI tooling, and also the integration of GPUs is relatively straightforward. There's a lot of scheduling help. Both NVIDIA and AMD do have operators available, although still the scheduling faces the issues that we just talked about earlier with the hardware heterogeneity. But other than that, also the inference engines are available in a containerized way. We typically use VLLM or SGLang, and also Kubernetes itself adapts to the AI tooling. There's, for instance, the inference gateway, which adds cache-aware routing to Kubernetes itself as a first-class citizen. We'll hear more about that later. And also, the resource allocation types are optimized, for instance, to better handle GPUs or other hardware in the cluster with what's called dynamic resource allocation. All in all, there's a full open source tooling stack, and no custom solution really is required to set that up. But for some use cases, there might actually be good reason to write it from scratch, and this is what Benjamin will tell you about now.
Thank you. Right, let's first look at the software stack for a basic inference setup. So in a minimal setup that every one of us could run at home, you would just need an inference server like VLLM or SGLang, which come containerized. And they already provide an API that is very similar to that of OpenAI. So it is compatible with most of the applications, be it a chat or a coding assistant. And this inference engine then uses the GPUs for the internal calculations. So that looks great and very simple. But of course, real life is not simple. And especially when you work in a larger company, in an enterprise context, then you have to zoom in what other components are actually needed in order to run such a platform. So typically, you would need some kind of routing component, either because you want to serve multiple models and only provide a single endpoint to the end users, or for load balancing purposes, so that you can spread the load across multiple deployments of the same model. And then two very important aspects for larger companies are authentication and billing. So when you work at home on your own computer and you installed VLLM or SGLang on your own computer, then you don't need authentication and also no billing. But of course, when you provide this as a service to others, then you need to deal with these tasks. And those are tasks that are typically that need to be integrated into existing solutions. And this is very individual to each company. And it's very difficult for VLLM or SGLang to provide universal solutions to these tasks. So this is why these three components, the router, the authentication, and the billing, are typically components that you have to write on your own. Let's focus on the router. So as already said, if you're a single user with a single type of request on a single server, then everything is fine. But as soon as you go from one user to multiple users, you have to think about, can they block each other? Would one user be able to slow other users down because long requests will be completed by the same batch that also serve other users' requests? This is particularly difficult to handle when you have different types of payloads. So when some users are using chats, where they write short questions and expect short answers, and other users use the LLMs for coding, where the IDE plugins would basically put all files they can find in the context window as long as it fits. So this is a huge challenge. And at TNG, we also have to deal with priority applications. So for example, Taya, the TNG AI assistant, is an interactive application that is kind of a first-class citizen. And it's also visible to some customers, for example, and also to some acquisition calls. So this is something that really should be going all the time and not be slowed down because some arbitrary user decided to send 100 requests at the time for no bigger purpose. Then we have a second set of challenges, which are the routing challenges. So we already discussed about serving different models with the same endpoint. Of course, you could either have a model parameter in each request that says, I want to be served by this kind of model. But there's also implicit model routing possible. So this means that there's some intelligent layer involved and some network that decides, this request seems rather simple. It can be served by a lightweight model that does not need many resources. And a different request might be more complex and needs to be served by a more powerful model. So this is only one part where we can optimize our resource usage. Second challenge is GPU utilization. Now we own the hardware, and we want that all our hardware is actually in use. And nothing would be worse than having hardware that is idling, because that is basically throwing money out of the window. Connected to that is the cache awareness. Calculations are expensive, and if it's possible, then we want to reuse the results from previous calculations for future requests. And this is, again, simple when you work at home on your own laptop, because then you are the only user, you have only one type of hardware. But when you have different hardware and you have to think about multi-node deployments, then also this caching is difficult. You need kind of a distributed cache, or you need to know in the router component how to route your requests so that you can get the highest cache hit rates. There are a few open source solutions, and actually the number is growing month by month. So NVIDIA Dynamo is, for example, a framework that is heavily focused on this distributed inference, and it's heavily optimized for NVIDIA components, of course. Then we have engine-specific frameworks like SGL Router or the VLM production stack. But what I find particularly interesting is what Lucas already mentioned, the engine-agnostic solution, a Kubernetes gateway RP inference extension. Basically, it's a separate Kubernetes resource that fulfills the task of routing the request to the optimum endpoint. And so it's not a deployment of some container image, but it's really a separate Kubernetes resource. And that could interact with any inference engine in the backend. But for these other challenges, like multi-user serving and also priority scheduling, we decided to write our own custom solution. So we use user-separate queues so that one power user cannot flood the system with their requests and block other users. And also we implemented latency-aware scheduling, which means we have some kind of target latency for inter-token latencies. So when you use a chat, then you can be sure that there's some minimum speed at which the tokens will arrive. And if this speed cannot be kept high enough, then the system will not accept other requests, simply because like this interactive agent is our most popular and highest priority application. And our findings for these scheduling challenges have also been published in blog posts on Hugging Face, so you can read them up and have a chat with us later. Of course, this was only the software side. And there are also physical challenges. And the biggest two are power supply and temperature management. The GPUs that we use, one of them draws 1 kilowatt power. We have 8 GPUs in one single server. We have several servers in the same room. There are not many buildings and not many rooms where you can actually operate such a big cluster. And once you have found the power supply, the power lines, then you still have to bring the power from the wall circuit to the GPUs. So you need some kind of power distribution unit. And then you're happy because you just found a very big power distribution unit, only to find out that's the wrong type and it is not compatible with the actual hardware that you bought. So those are real challenges. And second challenge, temperature management. 1 kilowatt input power means 1 kilowatt output power. Everything goes into heat. We basically built a very expensive heating system for our server room. And this is fine for the winter month, because we could rely on passive cooling from the outside. But during the summer months, we sometimes had to throttle down our systems because we were generating so much heat. There were already some air conditioning installed in the room, but that was not sufficient, and we had to install additional mobile cooling devices. And also some very DIY hacks for bringing warm air outside again. And these are the type of problems that we do not want to have to face every day. And that was the decision to move some of our servers to a professional data center. So we still own the hardware. We are still the only admins. The access is highly restricted, but we do not have to worry about power supply and temperature management anymore. OK, now we have our great GPU cluster. Now we can work with it. And there are many different applications that you can run on such a cluster. And those are just a few: TNG AI Assistant, TIA, the TNG Web AI Navigator. Both have showcases in the other building. Then we also did research on our GPU cluster. We constructed our own models. There's a separate talk going on right now in a different building. And of course, we can run benchmarks to find out which model performs the best for which task. And then there are, of course, many more tasks that we can solve with our AI cluster that are not noted down here, because they're just improving everyday life for all of our colleagues. Thank you.
Are there any questions to this first talk?
So how is the benchmark being done?
That's the second half of the talk.
Which benchmark do you mean?
For the LLMs, basically. So how can you check that it improved, for example, with the Chimera model?
Oh yeah, that's really the next talk.
Okay.
Thank you for the nice talk. I have a question concerning AMD hardware. Could you go a bit more into the details, what research is going on there, and whether you think that it's really truly an option to migrate away from NVIDIA nodes?
In terms of the AMD node, you mean? Oh yeah. So what we ran there is there's a tool. Incidentally, it's by NVIDIA. It's called, I think, Gen AI Perf tool or something. And then it has some generic ways how to test. And what we tested is short input and short output, and short input and some longer output. And we compared a lot of the metrics. So typically, you have time to first token, inter-token latency, and throughput per request. And we looked at this as a function of parallelity. So how much requests do we have at a time? And it showed that, I mean, it doesn't only depend on the hardware, right? The hardware sets the upper limit, but also software optimization. But with comparable setups, we found that the throughput, for instance, can be much higher on AMD as it would be for NVIDIA. But to be fair, I mean, the AMD nodes, they have, I think, the ones we tested had 240 gigabytes of VRAM, whereas the H100s had 80. So there's less inter-chip communication. So the comparison has to take a little bit with a grain of salt. But all in all, the throughput was more than competitive. I can show you some output later if you want.
But I want to stress that it's really also dependent on the software side. And you cannot expect that only because you run software on the NVIDIA hardware, it will run in the same way also on the AMD hardware. So you typically have to go through documentation for a long time before you have the optimum setup.
Thank you for the nice talk. So we, for our LLM at Heidelberg University, we noticed that loading different models takes a lot of time, and that if you have a model on disk and then some user requests a weird model and you load this took surprisingly long time. Do you experience something similar, or because for us it means we really want to offer fewer models basically and keep them basically running all the time?
Yes. So we do not typically dynamically scale up the number of models, but we rather keep the selection and also the number fixed, and then we don't have this problem. But also we experimented a bit, and for example, with the AMD node, we have quite a bit of RAM installed that allowed us to also load the entire model into RAM, and then loading from CPU RAM to GPU RAM is much quicker than reading from a disk system again.
Right. Any further questions? Yeah. Okay.
do you have any numbers on what your power overhead is? So for 1 kilowatt of compute, how much power do you have to put in for everything else?
Not off the top of my head, but I think the AMD machine has 8 kilowatt that it pulls peak load just from the GPUs, and I think it needs 12 peak load. Is this correct? Roughly?
Roughly, maybe.
I don't know, but we can look into the monitoring. I don't have it in top of my head.
And of course, the overhead is, like the relative overhead is larger when the system is idling, more or less, and when there's no real token generation going on, because then like everything is running, but there's no output, right? So at times of high load, actually the overhead is, relatively speaking, smaller.
Okay, but you do need more cooling then.
Yes.
Just not relative.
So it's still the more dangerous scenario. Yeah.
All right, we have time for one more question. No, then I think thank you so much, Benjamin and Lucas. I think you'll also be available after the next talk, and if there's any more detail or intimate questions you want to ask, then feel free to step up later. Yeah. So a round of applause for our speakers. All right, which brings us to the next half of this talk from Lennart Schiefelbein and Jonathan Dumenil-Rochemont. Now that we've known, okay, serving LLMs is actually quite resource intensive, right? So we want to serve the best LLMs possible, right? And that's like a reason why we need to evaluate them. So our next two speakers, Lennart and Jonathan, are going to tell you how you can benchmark your LLM and basically make the decision. Both of them have deep ties with the innovation hacking team. I think you already saw the innovation hacking show booth at the main building, but if you haven't yet, check it out. There's many interesting showcases there. You will be able to check out Tire. You will be able to maybe even navigate our new G1PO robot, maybe fight it, who knows. But for now, I think you'll get some valuable insights here. And yeah, Lennart has worked in various fields, including reinforcement learning, computer vision, and large language models. And Jonathan's main focus lies on the benchmarking and evaluation of large language models. And additionally, he's also involved in various projects in machine learning and robotics. And I think he is ready to go. So welcome our two speakers, Lennart and Jonathan.
Yeah, thank you very much. Welcome to Beyond the Score, your guide to benchmarking LLMs. So now we've seen how we deploy LLMs on a GPU cluster at TNG. The question we want to answer now is, how do we actually select them? And the reason why we started benchmarking was actually this question. So a year ago, we started this initiative to run our own benchmarks and to answer the question, which LLM is actually best in which field. And out of this, we implemented a framework to do this and also implemented a dashboard to distribute and to show the results of benchmarks. You can also check this out in our expo in the main building. But, well, before we get started, short intro from us, Jonathan.
Yeah, I'm Jonathan. Let's have a look first, what is an LLM benchmark? So at the basics, whenever we have a benchmark, we have samples. So these samples together form a data set. And what we do is we pass each of these samples into an LLM. This way, we get a completion. And now the big question is, are these completions any good? What we need to do is we need to assign some score to each of the completions. And in the end, we can average the scores, and we get an average score for our data set, which tells us if the LLM is any good. Now, let's take a deep dive. With benchmarking, we can measure several capabilities of LLMs. Today, we're going to talk about general knowledge capabilities, and we're going to talk about visual understanding capabilities of LLMs. Lennart, how can we benchmark general knowledge capabilities of LLMs?
Well, general knowledge capabilities are actually the first thing which has been, in a way, benchmarked when talking of or speaking of LLMs. So remember when ChatGPT became a thing and became popular, there were news reports out there claiming ChatGPT is better than 8th graders, 9th graders, college students, and so on. And the way this was tested in many cases was that maybe math Olympiad exercises or any other kind of exam exercises were passed to those LLMs. And the idea behind testing general knowledge of LLMs is actually asking an LLM exam questions in a way. And an example which we've brought to you today is Humanity's Last Exam, which is a pretty famous benchmark for general knowledge. And it consists of questions like this, like what is the standard Japanese pitch accent pattern of this kanji? Or questions about flags considered as matrices. So questions from many different topics. And this is actually also the first thing what to consider when looking at benchmarks. Jonathan just introduced it. What are the samples? And for Humanity's Last Exam, this is actually expert knowledge from many different fields, so from math, from physics, from humanities, social science. And the special thing about these questions and this data set, which makes up Humanity's Last Exam, it's actually compiled or a compilation of contributions from over 1,000 experts from those different fields. So these can be researchers, lecturers, and so on. So this is a really powerful way and a really high qualitative way to compile a data set for benchmarking because it represents actual human knowledge and thus actual human expectations. However, it's also the most expensive way to gather data. In this particular case, the authors had a pool of prize money of $500,000 to distribute among the contributors to encourage them to hand in example questions. So this is the sample part. Now, how do we feed those samples to the LLM? How do we ask the LLM such questions? And in Humanity's Last Exam, there are two ways to do this. The first way is to give answer choices, kind of a multiple choice pattern, where you ask the LLM to provide the answer as a letter, A, B, C, D, or E. So this is really easy to evaluate down the line when talking about scoring, because you simply have to compare what does the LLM put out and compare it to the ground truth. However, in Humanity's Last Exam, there's also another way how LLMs can answer those questions, and this is free text. So in this case, it says on this question about flags of African nations, Benin and Madagascar. However, this answer can be in many different formats. It can be JSON, it can be a list, and so on. And it turns out such questions or such answers are rather involved to evaluate. However, still, when talking about LLMs, the output typically is rather involved because you use it to generate text. So the question is how to score this, how to evaluate this. A really powerful tool to do this is LLM as a judge. Here the idea is, instead of going there as a human, as an expert, going through the answers and checking them, we take an LLM as a surrogate. This might sound counterintuitive at first. However, it turns out that this is actually a pretty powerful tool to get scalable and automatable ways to evaluate LLM output. So how's it done? We start with a completion, which we've seen earlier, which is Benin and Madagascar, for example, or text, whatever. And together, maybe with the input sample or a ground truth, we can pass it to our judge LLM. And this LLM is prompted in a particular way. So for example, here you can see the judgment prompt for, or a part of the judgment prompt for humanities last exam, which says, judge whether the following response adheres to question is correct or not, based on the correct answer below. And you then pass the respective information. And you ask the LLM to provide a score based on this. This score can be something like true, false, or a score between 0 and 10. There are different possibilities. In reality, or in practice, it turns out simpler is better there because you get more reproducible results. But that's the general idea of LLM as a judge. Still, the important thing about it is having it aligned with your own judgment or expectations in order to make sense. And so when using LLM as a judge in a benchmark or in an evaluation of LLMs, it's really important to engineer it. So you can engineer the prompt based on the scores. If it doesn't quite fit what you expect from your LLM, engineer the judge such that the judge is aligned with what you expect. Another way which you can use to improve judgments is to split the task into smaller judgment tasks in order to make it simpler and more scalable and reproducible when using it as an evaluation tool. So there are a few intricacies when building such a tool and building a judge as an LLM. But if you have done so and if it's aligned, you get a scalable and automatable way to evaluate also complex responses of LLMs. So now that we have seen how to judge the output of an LLM, if it's on the one hand really simple, like A, B, C, D, E, or a bit more complicated, like when it's returning free text. Let's now have a look at the capability of visual understanding and shift a bit our focus on a benchmark which we created on our own to assess visual language models.
Yes. So, we at TNG, we have a use case actually, where we want to extract information from documents. Here we have an example. So this here is a delivery note. In this case, we have some address, we have some items, and we also have item quantities and units also. What we would like to do is we would extract the information from this document in a systematic way. So what we can do is we specify a JSON schema, and in this JSON schema, we define what elements of this document we would like to get extracted, and then we pass the document to a visual language model together with a JSON schema, and ideally, we get the JSON, which tells us all of the addresses and the items and the other things that we would like to get extracted. Now, let's take a deeper look at the samples, because this benchmark, as Lana just said, we developed on our own. So what we wanted to do, we wanted to measure how good are LLMs, or vision language models, on these OCR tasks, specifically in German. So we had a look at the literature, and we found out that there are actually no good OCR benchmark data sets specifically for German. So we engineered our own. The first thing that we did is we generated the data that we want to fill in the document. So here we have the JSON with the ground truth of our document. And the next thing that we did is we generated PDF templates in which we infill the data. So they all look a bit different. They all have different layouts. The third thing that we did is we want to have about realistic data in our benchmark. So we generate scans of these documents. So we perform an augmentation. So here we have the original document, but we adapt it. Maybe we add some noise. Maybe we make it look more like a scan. We can actually use like libraries from open source to do just this task. So in the end, our data sets consists of elements that look like photos or like scans. And in the end, what we can do is we compare the information that the LLM extracts to the ground truth that we know because we generated the documents ourselves. So this is the OCR benchmark. Let's take a deeper look on the data augmentation side. So what we did is we started with our real-life use case, and then we added more data by performing these augmentations. So for example, by making it look more like a document, like a scanned document, or like a photograph. So we performed this augmentation. But whenever we do so, we need to take care that we actually do some validation also. It's very important that the original data from our use case looks similar to the LLM, like the augmented data. So we need to make sure that the output of the LLM is similar on both the original and on the augmented data in order to make sure that our benchmark is actually realistic. So now we had a look at a benchmark for general knowledge and also at a benchmark for visual understanding. Leonard, what else do we need to consider when we look at a benchmark result?
Yes. Looking at benchmarks means looking at the quality of LLMs, essentially. So this is what we did. We looked at which LLM is best in the capability of our interest. So we had this example of general knowledge. We had this example of visual understanding. There are many more benchmarks for all the other capabilities which we are interested in. But that might not be all of it, or that's not all of it. You also have to consider cost and latency when selecting benchmarks to deploy on a cluster, to roll out to 900 developers or 900 colleagues at TNG, for example, or also if you want to choose an LLM for your agentic use case, for example. So cost is something to keep in mind. You might not just go for the best LLM in a particular capability, but you rather consider which is actually the best LLM in my cost tier, which I find acceptable for my use case. And of course, last but not least, what to consider is latency. In many cases, this boils down to, do I need a reasoning model or a non-reasoning model? Because reasoning models, of course, they produce this think trace, and it takes really long. So the question is, do I really need this kind of intelligence for my task? And in general, the question, how long can I wait on my response? I can look up statistics. How long do I usually need to wait on a token? And so on. So do not always look at the benchmarks on the leaderboards. Always also keep in mind, what do I have to pay for it and how long do I have to wait for responses, and make a decision based on these 3 dimensions. So benchmarks, well, they are a representation in a way of capabilities, and they're an approximation on how good LLMs are in particular use cases. So let's maybe do a reality check, Jonathan.
Yeah. Of course, we have all the benchmarks, we have these very cool scores. But when we look at them in more detail, we notice some issues. So the first thing that we have is that models get stronger over time. And what that means is that we also need to update our benchmarks, because a benchmark from 2 years ago, basically every modern model that is any good can basically ace them. The other reason why that happens is because we have data contaminations. So we have many benchmarks that are open source, and eventually they will get leaked into the training data of modern LLMs. So you always need to update also your benchmarks because of this. The third thing that we have is we need to account for prompt variations and also for the inference parameters. So different models like to be prompted ideally with different temperatures, and also different prompts might work better for some LLMs rather than others. When you perform benchmarks, you also need to account for these. You either need to fix a temperature, or you need to say, okay, I will optimize the temperature for my LLM. And lastly, another thing is actually that in many benchmarks of the literature, we found flawed reference solutions. So we have cases where it's clear how we should perform the evaluation, but actually the reference solution is wrong. So this will affect benchmarks. But there is a way forward, because ideally what we should do anyway when we want to pick an LLM is we should perform some evaluation of our own use case. Leonard, how do we do that?
Yeah, so what we do or what we talk about when talking about benchmarks, it is talking about measuring capabilities or generic capabilities of LLMs in rather broad fields. However, your use case usually isn't generic, it's rather specific. You have a specific workflow, you have a specific use case for the LLM. And that's why we like to make this distinction at TNG or in our benchmarking team between benchmarking and evaluation, where evaluation is really about your particular use case. The cool thing, though, is that the inner workings of an evaluation and how to set up an evaluation pipeline is pretty similar to how to set up benchmarking. You always also think about your samples, your data first. You think about how to pass it to an LLM and how it's completed. Well, that's usually your use case. And you also think about how to measure the results. Let's start with the samples. The samples or the data should always represent the way your user interacts with your system, where your LLM is applied. So what does this mean? This means if you have an agentic workflow, look at the traces of your application. How does the user interact with your system? What's maybe going wrong? Where are the pain points? And you can collect them, and you can retest them with your system, see how are the results. And that's actually a pretty good way to kind of bootstrap your evaluation by starting with the data from actual user interactions. Now we can pass them again and again through our pipeline if we have, for example, improved our prompts and so on. So this part of generating the completions, this usually comes from our use case. The next interesting thing, apart from gathering the data, is of course making up our minds what do we actually want to measure? How do we want to score the evaluation? Because this encodes our expectation towards LLMs, towards our system. And a good way to define a metric is to think about the criteria. You can think about task completeness. Is the task which I've given an LLM actually completed? Were the tools called correctly when using the LLM? Were the tools parameterized correctly? Did it maybe select more tools than required to solve a task? Is each and every step of an agentic workflow relevant? How's the tone of voice? And all these criteria you can evaluate with metrics which we also know from benchmarking. For many of those, you can use LLM as a judge, for example. You can also use deterministic checks. For example, you always expect a particular tool to be called. You can deterministically check that. And based on this, create a collection of metrics which represent your expectation towards the system. Now, looking again at the samples, because we've started with a few examples of user interactions, maybe 50, maybe 100 if you're good. This might not be enough. So you might observe some statistical variations when running your evaluation, some flakiness maybe. And a way to mitigate this is extending your data. In our OCR benchmark, we've seen how we did this to generate a set for an example set with German invoices, German delivery notes, because we lacked them. The same thing you can do with your own data. You can think about how to introduce variations in the data set which you already had. This can be reformulate this question, asking an LLM to reformulate questions. If you know how to do it in your particular use case, built-in synthesization of data, and of course, fill the gaps which you observe when users report flaws and pain points with those data, with those user reports. And this way you can extend your data and gain more statistical stability when doing evaluations, and thus be more confident that your evaluations actually represent and are aligned with your expectations towards the system. So to sum up, evaluation consists of collecting samples, collecting the data, evaluating our system with them, and eventually scoring it with metrics which represent our expectations toward the system. So, Jonathan, what have we learned today?
We learned quite a lot today. So first of all, we had to look at what benchmarking is. And in particular, we had to look at benchmarks for general knowledge capabilities, and we also brought a use case for visual understanding capabilities. After that, we discussed the quality, cost, and latency triangle. With benchmarks, we measure mostly the quality of LLMs. But don't forget the constraints of your use case on the latency and on the cost of the LLM usage as well. And finally, we briefly discussed how to perform evaluations of LLM systems. You can use these evaluations, or you should perform these evaluations to improve your system and to make your users happier.
And with this, thank you very much for being with us, and enjoy the rest of the Big Tech Day. Thank you very much.
Awesome. Thank you so much for the talk. So, questions? Then I'll quickly lead with one because I also want to ask one. Do you maybe have an estimate of how much the prompting can influence the result of a benchmark? So if I basically ran the same benchmark on set models, but did not optimize the prompt, would that be like a 5% difference, a 50% difference? Could I actually make big mistakes there and choose the wrong model, or is it rather negligible? And yeah,
it depends, I would say. So there are examples where, for example, where reasoning tasks or kind of brain teasers have been tested, and small variations in the prompts have been introduced, and it was or turned out that the difference can be enormous. So some of the models seem to be trained on a particular way of formulating certain questions. So they perform only in one variant of a particular question well, and the other then they decrease. And for other models, you don't really see it. So this was this kind of brain teaser math-like problem. For other capabilities, for other applications, this might be different. So I would really say this depends, but this is actually a factor to keep in mind. And this is also why we encourage doing evaluations, because those benchmarks can only give a hint which model might be good, but sometimes they also might be misleading. For example, if a model is trained with a particular to adhere to a particular, or to be particularly good for a particular system prompt, then benchmarks might turn out not so well compared to other models. So it largely depends. Yeah.
So if you choose the same model as evaluator for compared to the producer of the output, versus like choosing different models, like does this make a difference? Like is the evaluator preferring like itself basically over other models?
Ideally, what you want to do is you should fix one evaluator and then use it for all the LLMs that you test. I think there's some research on this very question, but we don't have any data on it, I'm afraid.
Yeah, so in the past, it used to be that you don't usually. It was said to not judge the model with itself. However, nowadays, I would say rather keep the judgment task simple and rather make sure that the judgments are consistent, and then hopefully this effect doesn't play into or isn't too bad. And ideally, the judgment itself, the judgment task itself, should be much easier to solve than the actual task.
All right, further questions?
I think there's one over there.
So, yeah, my doubt is also related to judging. So my understanding is that you're basically building a binary classificator based on the judge in the middle. So you pass, then it becomes true or false, depending on whether it was correct. And then iterate until that's correct, or is it more complicated? Because it's a bit confusing to have, the AI model as its own validator.
I'm not sure if I got this question correctly. So, well, of course, you can improve your model based on judgments, and this is probably what you also use evaluation for. However, you always need to make sure that your evaluations are still aligned with your own judgments. So it's always a good hint to still have a look and to vibe check your modifications of your system before finishing it. I'm not sure if this really answered your question.
Okay. We can talk in a bit, yes.
Yeah. All right, time for one more question. All right, Dan, thank you so much. Thank you also, Benjamin, Lucas, Leonard, and Jonathan for your joint talk. If you have any further questions, feel free to come here. Otherwise, enjoy the rest of your big tech day.